Hello, my name is Nicole Campos, and the experiment I chose to discuss is the synthesis of a 2,5-bis terp-butyl methyl silyloxyfuran and its reaction with benzene. This is a three-part reaction where the compounds in part A and B are synthesized prior to the experiment in part C, as can be seen below here. I'll be discussing the reaction that takes place in part C, which is the synthesis of 2-methylnaphthalene 1,4-dione. So scale and optimization. The reagent N-butyllithium is highly flammable, therefore making this experiment not likely to be reproducible on a larger scale. It's not an expensive experiment to reproduce. Purchasing inert gases and other materials can be done at a relatively low cost. And in this experiment, the first two reactants were in fact synthesized in the lab prior, instead of needing to purchase the reactants to then make the product 2-methylnaphthalene 1,4-dione. The reactants 3-methylfuran 2,5-diol bis oxy bis tert butyl dimethylsilane exhibits enhanced stability characteristics towards water, methanol, oxygen, heat, and buffered silica, which also facilitates multi-gram scale preparation. So the checking process, the reaction was checked by Dave Charbonneau, Jordan Thompson, and Sarah E. Reisman. I was able to find that Jordan K. Thompson was the user responsible for uploading NMR spectroscopy data for the reactants and the products made in the third reaction. And listed in the notes section, there were also mentioned that the checkers listed that inert gases that could also be used in the experiment included nitrogen in place of argon, which was used in the experiment. And lastly, an HNMR of the product before and after light exposure was provided by the checkers. Reaction apparatuses include a 500 milliliter 3-necked 24x40 round bottom flask with two 24x40 glass stoppers and a 24x40 glass gas adapter with a gas inlet, as can be seen in the upper right hand image over here. There was also use of one glass stopper that is replaced with a 24x40 rubber septum in this image over here. And later in the experiment, this second glass stopper is replaced in exchange for a 24x40 Teflon thermometer adapter that's equipped with ultra-low temperature glass thermometer. And in image C, we can see in a 1,000 milliliter single neck flask that was used, round bottom flask that was used, 24x40, and later in the experiment, the flask is equipped with a 24x40 plastic stopper joint wrapped with parafilm over here. Reagents and starting material. There are special precautions that are taken when handling N-butyllithium. So prior to the addition of the N-butyllithium, it's titrated using 98% diphenylacetic acid, which was recrystallized from anhydrous toluene prior to its use. And a cannula is used when adding large quantities of N-butyllithium in the experiment because this is generally viewed as a safer alternative compared to other addition methods. The excess reagents in this experiment include 3-methylfuran 2,5-diol bisoxy bis tert butyl dimethylsilane, as well as N-butyllithium, and both have 1.25 equivalents. The limiting reagent in this experiment is 2-iodophenyl trifluoromethane sulfonate, which has 1 equivalent. So now I'm going to get into the procedure a little bit. To start, the procedure begins with a 500 milliliter 3-necked round bottom flask, as I showed previously, and can be seen in this image over here. It contains a Teflon-coated magnetic stir bar. and the apparatus is flame dried under vacuum and purged with inert gas argon. And the argon in this instance was used as it was received, and nitrogen gas was dried via passage through a dry rate column prior. And this process is performed in a triplicate. This setup is maintained under slight positive inert gas pressure throughout and allowed to cool to ambient temperature of around 22 degrees Celsius. So a glass stopper over here is replaced with a 24 by 40 rubber septum at this point in the experiment, and the flask is charged with 19.6 milliliters of the first reactant via a syringe transfer, and then 7.74 milliliters of the second reactant via a syringe transfer. And both 1 and 2 reactants are degassed prior to the addition through exposure to a vacuum at room temperature for 5 minutes before transferring to a syringe under a positive pressure of inert gas. And again, this positive pressure is maintained throughout the syringe transfer. So next in the experiment, 171 milliliters of tetrahydrofuran was passed through an activated alumina column before its use, and then it was transferred into the flask using an 18 gauge cannula. And at this point, the last glass stopper over here is exchanged for a 24 by 40 Teflon thermometer adapter containing an ultra low temperature glass thermometer, which ranges from -100 to 50 degrees Celsius. And that can be seen in figure 6b with the tetrahydrofuran at the bottom over here. Stirring is then initiated at 650 rotations per minute, and the reaction flask is submerged in an acetone dry ice bath and cooled until the internal reaction temperature reaches -70 degrees, and this process takes about a half an hour. As can be seen in the image here, we have the acetone with the dry ice bath. Then 43.3 milliliters of N-butyllithium is added via cannula for safety and syringe pump with a 60 milliliter syringe over a span of 20 minutes. The internal reaction temperature initially reaches -50 degrees Celsius, and then about halfway through the addition reaction, it turns a light pink color. And that's this light pink color here in this image C. Following the completion of N-butyllithium addition, the internal reaction temperature now reaches -60 degrees Celsius, and the reaction is maroon in color, as can be seen in the image down below. Then the reaction is stirred for 10 minutes and quenched by dropwise addition at about 1 drop per minute of 10 milliliters of saturated aqueous ammonium chloride solution using a syringe. There is a small exotherm reaction that takes place, reaching -54 degrees Celsius, and the formation of a white precipitate is observed. Here we can see the white precipitant is forming after the ammonium chloride is added. The reaction is then warmed to ambient temperature for about an hour, at which point the reaction mixture then turns a bright yellow color with precipitate still being present, as can be seen in figure 7b. Over here, the bright yellow color of the reaction after it's warmed. The reaction mixture is then transferred to a 2,000 milliliter separatory funnel, and the reaction flask is rinsed with 100 milliliters of both ethyl acetate and deionized water during the reaction purification process. The mixture is further diluted with 450 milliliters of deionized water to dissolve the precipitate, and the mixture is extracted with ethyl acetate twice, each time being with 200 milliliters. The combined organic layers are washed with 2 moles of HCl 3 times, each time with 300 milliliters, as well as once with 30 milliliters of saturated aqueous sodium bicarbonate, once with deionized water, and last with brine. The organic layer is dried with 24.7 grams of magnesium sulfate and filtered through a 350 milliliter 9.5 centimeter sintered funnel, medium grit, into the round bottom flask. As can be seen in this upper right hand corner, this is the sintered funnel, which would be placed on top of here. And the flask is placed on a rotary evaporator, and the solvent is removed, resulting in a yellow solid formation, which can be seen in figure 7C. The crude product is then transferred into a 500 milliliter round bottom flask, and residual solvent is removed under high vacuum and ambient temperature for 3 hours. After 3 hours, 50 milliliters of hot hexanes is added at 60 degrees Celsius and transferred into a round bottom flask equipped with a Teflon coated magnetic stir bar and stirred at 400 RPM. Lastly, the crude mixture is warmed to reflux and heating is maintained until the crude residue completely dissolves, which takes about 5 minutes. The experimenters recommend that during this part of the procedure, the flask is equipped with a reflux condenser connected to a nitrogen line, and the appearance of crystallization halfway through dissolving the crude residue can be seen in figure 8A over here. So this is when it starts to reflux. A 24 by 40 plastic stopper joint wrapped with parafilm is then placed on the flask. As can be seen in this figure here, 8B, we see the plastic stopper above. The flask is then removed from the heating mantle. So this heating mantle is removed, and it's allowed to cool to ambient temperature. And at this time, crystallization has occurred, which can be seen in this figure as well, over here. Then the flask is transferred to a freezer of -20 degrees Celsius for 12 hours, and after it's removed and filtered through the sintered funnel again, eluting with a minimum volume of cold hexanes to give small, bright yellow crystals. And the solid is transferred into a 50 milliliter beaker with a magnetic stir bar and stirred at room temperature for 5 minutes in hexanes, about 4 milliliters per gram of material. The crystals are collected by filtration through the sintered funnel, eluted with a minimum volume of hexanes. In this case, 20 milliliters were used, and the yellow solid results is then dried for 3 hours under high vacuum and ambient temperature, resulting in the product formation of 2-methylnaphthalene 1,4-dione, which can be seen here in figure 8C. We have the finalized product. The overall yield was 84% with a 98% purity of the 6.18 grams that were collected. And it's also noted that a second run on half of the reported scale yielded 2.63 grams with a 72% yield and, again, 98% purity of product. Characterization and proof of purity. So the purity was determined to be 98% by quantitative HNMR spectroscopy, and it was done so by using 10.5 milligrams of the product, as well as 4.5 milligrams of 99% 1,3,5-trimethoxybenzene, and a C13 NMR was also conducted. So here's the HNMR, and here's the C13. In the notes section of the report, it was also mentioned that the product was determined to be light sensitive, and it's recommended that the product, specifically the solid form, be stored in the absence of light, and exposure to the compound to light should be minimized during the workup. Safety notes and hazard warnings. Safety notes included were regarding the cannula in order to add large quantities of N-butyllithium. This was seen as a safer option due to how highly flammable the substance is and how reactive it is, because N-butyllithium poses a danger when using the chemical in a lab setting. In the notes section, the point number 1 stated also that the standard safety notes and hazard warnings when conducting an experiment with potentially dangerous chemicals be listed, and a thorough hazard analysis and risk assessment should be carried out with regard to each chemical substance and experimental operation. on the scale planned and in the context of the lab where the procedures are then carried out. So it was all listed in the notes section, and in the case of this procedure, they mentioned that the risk assessment should include, but isn't limited to, an evaluation of the potential hazards associated with each chemical. And there was also a disclaimer section which mentioned working with hazardous chemicals and their liability. So here we have the mechanism for the reaction that took place. We have N-butyllithium being added first, and this is the transmetallation reaction where iodine is replaced by lithium. And then secondly, we have tetrahydrofuran in negative 78 degrees Celsius conditions taking place is then a Diels-Alder reaction in the following steps. Overall, the synthesis could be conducted in our chemistry lab based on the small scale which it's conducted at, however, with the added precaution that hazardous material is handled properly. The authors of this report were Jessica Budwitz and Christopher Newton, who belong to the Department of Chemistry at the University of Georgia. Jessica Budwitz received her BS in chemistry in May of 2022 from the University of Georgia, where she worked in the Newton group studying the application of Diels-Alder strategies in total synthesis. And Jessica is currently pursuing her PhD. Christopher Newton studied chemistry in New Zealand and received his PhD at the Australian National University. And here are my listed references, and thank you for listening.